All right, everybody, welcome back. So last time we finished up talking about autonomous equations and how we can start to visualize solutions to nonlinear ODEs a little more cleanly than trying to solve for them explicitly or solve for their solutions explicitly. So instead of algebraic solutions, we wound up using graphical solutions. And in that same vein, we're looking for more graphical solutions because that seems to be a reasonable way to go, or a reasonable approximation, or a reasonable way to approximate a solution. In the previous section, we had a very qualitative description of, or qualitative graph of what solutions looked like to certain nonlinear PD or ODEs. And what we'd like to do in this section is try to extend that methodology a little bit and see how we might be able to go past autonomous differential equations and create approximations of just an arbitrary first order ODE. And this is where numerics come into play. I note here right at the beginning of this section that we are skipping section 2.6 on exact differential equations, I believe, because frankly, that doesn't show up too often enough to make it worth discussing in this context, because if you are going to see it again, you will discuss it from scratch in that setting anyway. So I'm skipping that. What we're going to do this time is go straight into section 2.7. And this is on numerical approximation, and specifically we're going to get a first order scheme called Eulers Method, specifically the Forward Euler Method. Now, the way to think about how this method works is to imagine that we are actually trying to reconstruct a differential equation by hand. And remember, back in chapter 1, there was this concept of a slope field. And in other words, what winds up happening in this setting, we are able to go to every point of the plane and try to, and not try to, but actually figure out what is the slope of our solution supposed to be at each of these locations. And we wind up with a nice little graph or plot that looks like this. So specifically, if I had a solution that went through this point, then it would have to be tangent, that was a terrible description, it would have to be tangent to each and every one of these slope lines as I constructed the solution. It may not pass through all of the ones that I've drawn, but no matter where I go, if I choose another point to represent, then the slope must match what the slope field says at that location. So let's go back a step. Let's actually try to think about what would happen if I were to try to actually draw that solution by hand. Well, I would start, I would have to start at my initial condition and then take a tiny step forward in the only direction that I know, and that's based off of the slope field. So I take a tiny step forward in the t direction, so here's t0, and then I'll go to a new step, t1. And then I'll ask, what does the slope look like at that location? And that was also kind of terrible. Here we go, this might be a little bit better. Now I'll go ahead and draw for another little time step what my solution looks like if I use that slope. So I'm just making a whole bunch of lines in effect. And if I come down a little bit further, it should flatten out a little bit, then it'll come this way. And I'm just asking at each step I take, or at each location, ask what the slope of my solution has to be, and then take a step forward along the tangent line of the function at that spot. And then I repeat that process. I ask what the slope is, and then take a step forward along the tangent line. And so that means that for whatever solution I have, right, here's my differential equation, dy dt equals f of t, and then I give it an initial condition, t0 by y0, then the tangent line of my solution, right, my solution is going to be approximately equal to y at t0 plus whatever the or I should go down to the next line, plus it should be plus y prime of t0 times t minus t0, right? This would be my tangent line approximation, right? We remember this from Calc 1. But I know what this y prime is by my differential equation. So specifically, y of t is approximately equal to y of t0. Hey, I actually know what that guy is too. That's my initial condition, so y0 plus f of t, and that'll be, arbitrary t, this is specifically at the initial condition, times t minus t0. And this is what the tangent line to my solution has to look like at my initial condition. So that means that I know what my solution should look like. I know I can approximate this in a very small neighborhood of the initial condition. And that's what I have in the notes down here, that there is this nifty little way of approximating that solution. And I can actually scroll down a bit further. Oh, shoot. I didn't actually write it down in here. This is amazing. Okay, awesome. No, this is great. It means we can go ahead and do this from scratch. So let's go ahead and do this example here. So for example, dy dt. This is equal to, 3 minus 2t minus 1/2 y, and I'm going to give it the initial condition y of 0 equals 1. So this is an initial value problem. And we can go ahead and try to solve for the tangent line at this location. And that will be y of t is approximately equal to y0 plus whatever 3 minus 2t minus 1/2 y evaluates to at 0 by 1. And I'm going to multiply that by t minus 0. Or t minus, I'm putting in the initial conditions, I might as well. So that guy goes away, and this is now a 1. There we go. So that means that my tangent line, my y solution, is approximately, it's approximately equal to this line. If I use t equals 0 and y equals 1, this is 3 minus 1/2, so this will be, 5/2 times t, right? T minus 0 is just t. So this is my tangent line approximation, and I can use that in a very small neighborhood to figure out what my solution looks like. So if I go back up to this picture, I'm effectively just looking at this first little line segment, trying to figure out where the next location is in my stepping. So I could use whatever t I want here, but I think you can see pretty clearly if I make too large of a step. If I go I don't want the eraser, I want the goldenrod pen. There it is. If I take too large of a step, then I've gone way off track, right? I can kind of tell that my solution needs to follow this kind of curve, and this yellow goldenrod curve is not going to follow that at all if I take too large of a step. Therefore, what I should do here is I should use a step that is very small. So I should say, okay, go from t0, so t0, and add a very small change in the step, in the t step. So that will go ahead and assign a specific number. So this is something that's either given or that you can go ahead and specify. And the textbook actually uses a step size, and they call it h. And h should be small. This should be small. And what I mean by small, I mean small relative to whatever measurements you're making. Usually, because we're working in a computer, this delta t is allowed to be very, very small. We can go ahead and specify something like 10 to the minus, 12th or something, before the computer starts to throw errors at us, something about a machine epsilon. Right, so let's go ahead and just say this is, 10 to the minus 3. So we could step a little bit here. Actually, what I use in the example is a step size of 1/5. Yeah, so let's go ahead and follow the example in the notes. So 1/5 is approximately, it is 0.2. So I can go ahead and say that y at 0 plus 1/5, right, this should be equal to 1 plus 5/2 times 1/5. And now you see why I used that step size as my example. There's a 1/2. So this tangent line approximation tells me that my solution should be very close to 3/2 as I take that step forward. Now, I can go ahead and take this output and apply the same process. So iterate this at 1/5, 3/2 now. So find a new tangent line, and so on. So that's what this process is up top. I'm going to go ahead and take my, I'm going to take my new point, which I'll do this in blue. Come on, do that in blue. So my new point here, I'm going to take a step in this direction based on a tangent line at that location. So to see how that might look, we'll do one more iteration and then say, well, this sounds like a job that's suited for a computer, because it is. So y at, okay, I'm going to go another step forward. So this is plus 2 times the h. So this will be equal to y at 1/5 plus another 1/5. And this is approximately y at 1/5, right? I have to make a new tangent line approximation, plus this will be f at 1/5 by 3/2 times another tiny step. So this will be the 1/5 again. And I'm going to go ahead and compute that real quick. Well, I got the approximation for y of 1/5 last time. That should be 3/2, right? That's based on that point right there. That's my approximation. Now, f, remember, this is 3 minus 2t minus 1/2 y. I'm going to evaluate that at the approximate point, 1/5 by 3/2 times 1/5. So 3/2 plus a new slope. What is this new slope? It's 3 minus 2/5 minus 3/4 times 1/5. Oh dear Lord, this really is a job for a computer, isn't it? 3/2 plus, okay, so 15 minus 2/5. Oh, son of a gun. Get out of here. Okay. 15 minus 2/2, that'll give me a 13/5 minus 3/4. Yes, I could put this into a calculator, but that'll be in the next video. So if I do common denominator here, so no, I know I'm going to go to 20 in the next one, so I'll leave that for a second. So 13 times 4 is the number of cards in a playing deck. 52 minus 15 over 20 times 1/5. Okay, 3/2 plus, okay, that'll be a 37 over 20 times another 5th. Oh dear, yes, this is lovely. I'm having a wonderful time. Are you? Let me know in the comments. And finally, that means we're at, what, I multiply that by 50, so this is 150 plus 37 over 100, and that is, no, not 200, that is 187 over 100, which is, in decimal form, 1.87. Phew, okay. So that would mean my next approximation, so I'm starting with an initial condition at 0. So at n equals 0, I have my initial condition. t0 equals 0, y0 equals 1. If I go to the next step in my iteration, we've picked up an approximation of 1/5 by 1.5, right? That's 3/2. And we just went to the next iteration. This is another 5th away from 0, so this is 2/5 by 1.87. And I can continue that process however long I would like. So what's the general scheme? Well, Tn, the next iteration in the scheme, is going to be whatever t0 was, and I'm going to add in however many steps I took, so n times h. So I took n steps away from t0. Now, yn is a little bit more complicated. It's going to be based on what the previous iteration was, plus what the slope is at that previous iteration, and multiply that by my step size. And these two things together give us a collection of points that approximates our solution. The lines that I drew in between are totally artificial, right? I'm just using a tangent line to approximate my function. So all I'm doing is connecting the dots based on this scheme, and this is for n greater than or equal to 0. And this is what is known as the Forward Euler Method. And this is a starting point for numerical analysis.